Hey friends, this is Vidhan. Welcome you to my channel. Today we will see a problem from December 2012, question number 43. In the opamp circuit shown in the figure, Vi is the sinusoidal input signal of frequency 10 Hz and V0 is the output signal. That means input signal is the AC signal because frequency is only possible for AC signal and not for DC. The frequency of DC is 0 and that is why the output signal will also be AC signal. The magnitude of the gain and phase shift respectively close to the values A, B, C, D. That means we have to find magnitude of the gain and the phase shift. These two things we have to find for this given op-amp circuit. I have drawn this circuit on my board. So here is our given circuit in the problem. This is feedback resistance and I can call this feedback capacitance because these things are connected in the feedback circuit. I have to find the gain of this circuit, and the first criteria is that to find the gain we have to recognize this circuit. We have to recognize that whether this circuit is inverter or non-inverter or integrator or differentiator or logarithmic amplifier or anti-logarithmic amplifier. So whatever circuit it is, we have to first of all figure out, we have to know, we have to recognize this, and when we have recognized the circuit, then I can write down the output formula, and always in the output formula there is a scaling factor, and that scaling factor is the gain. So we can find the gain when we understand the circuit. So for that, let us see the circuits, standard circuits one by one, and compare the given circuit and try to come to a conclusion that what circuit this is. So the first of all, let us take integrator. This is called ideal integrator circuit, and we can see comparing with the given circuit that our given circuit is not ideal integrator circuit because they are not similar. Here there is additional resistance, but here there is no resistance in the feedback circuit. So that's the difference. Now let us go to another integrator circuit, that is called practical integrator circuit. This is called ideal integrator circuit and this is practical. Why practical? Because this is used practically, but practically this is not used. And why not used? Because even when there is no input voltage, there is an output voltage, and that is called error output voltage. But in this case, when there is no input voltage, there is no output voltage. That means that error output voltage is reduced by additional circuit. Let me show you. See here, the practical integrator circuit has this additional resistance that is parallel to the capacitor in the feedback circuit. This is it, and this helps to reduce the error output voltage when there is no input voltage, and this is called practical and this is called ideal, but their output formula is same. Okay, the output formula if you write down, that is minus 1 by R1 CF integration of V input from 0 to T dt, and for this also it is same, minus 1 by R1 CF integration of from 0 to T V input dt, obviously plus C and here plus C. That means for both the circuits the output formula is same. That means this extra feedback resistance, if I write down RF, this has no effect on the output voltage formula, but yet this is used practically. Okay, now comparing the given circuit with the practical integrated circuit, we can see that there is again a mismatch. The mismatch is where the capacitor is upside here and the resistor is downside, but here the resistor is upside, capacitor is downside, and that's the problem. So we come to the conclusion that the given circuit is not practical integrated circuit also. Okay, now we go to differentiator circuits. So let us take differentiator circuit. This is called ideal differentiator circuit, and we obviously can see that our given circuit does not match with this because here is only a resistor, but here in the feedback circuit there is a capacitor and a resistor. So this is not the circuit. So let us see practical differentiator circuit. Why practical? Because this is used practically. In practical this is not used because there is a problem, as I told you just before. Now if I compare the given circuit with the practical differentiator, then it looks like they are same, but actually they are not same. Yes, in the feedback part they are same, because here in the feedback circuit a capacitor and resistor are there, and here also a capacitor and resistor are there, and also the capacitor is upside, resistance is downside, and here also capacitor is upside, resistance is downside. So they are pretty same with reference to the feedback circuit, but before the operational amplifier here there is just a resistance, but now there is a resistor and also a capacitor. So here the difference comes, and that's why we again conclude that the given circuit is not a practical differentiator circuit. So what circuit is this? We have to come to a conclusion, otherwise we will not be able to find out the gain. So let me tell you directly that the given circuit is actually inverter circuit with feedback. That means this circuit is actually a inverter circuit. An inverter circuit is like what? This. Now one may ask or one may raise a question that actually this feedback circuit doesn't look same as here the feedback circuit. But let me tell you that if I find out the equivalent impedance of these two, capacitor has a effective resistance, and we know resistor has a resistance, and if we take the equivalent of these two, then they will become one. Let us say that is Z. Z is the effective impedance, not resistance. Generally it is called impedance. So for both these there is one impedance, and that is Z, that is equivalent impedance. The same circuit I have drawn. So here is a resistor, here is a resistor, input going to negative terminal, and there is a feedback circuit that is containing Z, and I can say that this RF is equal to Z. That means if this feedback resistance I make equal to Z, then this circuit is exactly same to this, and this is inverter circuit. Why? Because input signal is going to the negative terminal. So this circuit is actually this circuit when we make the feedback resistance equal to Z, and Z is we have to find out. Now what is the output? Output is minus RF by R1 into V input. We know that this is the output for inverter with the feedback. Now since here the feedback resistance is actually Z, that means the equivalent impedance of these two, so I should write this is minus Z by R1 into Vin. Now in our problem it says find out the gain. So this much is the gain, and this is what we have to find out. Now one more thing, it says that find the magnitude of the gain. That means we have to find the mod of this, and the mod of this is what? Only Z by R1. So this is what we have to find. Now R1 is known. Now for the same circuit, this is 1K, so I make it 1K. I will find Z, equivalent resistance of these two, and I will put it here. So this circuit is same to this, and gain R1 is known. From here just we have to find this Z, this much, then we will be able to have the gain. So we have to find this Z, that is gain. Now what is the situation? The situation is that (0.01 microfarad this is 10k, and we have to find the equivalent impedance of these two. And the signal is AC signal, because I told that when input is AC, then the output will be AC, and a fraction of output will go through this feedback circuit. So we have to find the equivalent impedance when the signal is AC. Now we know the equivalent impedance when they are in series. So when a resistor and capacitor are in series and the signal is AC, we know what is the equivalent impedance. Equivalent impedance is Z, and Z is equal to 1 by root over R square plus XC square. R square plus XC square. And what is XC? XC is actually 1 by omega C. XC is the effective resistance of the capacitor. But now we have to find the equivalent when they are in parallel and the signal is AC. So this is what, and what is the equivalent resistance formula or equivalent impedance formula? That formula is, now since they are in parallel, so I have to write down the formula of equivalent impedance when they are in parallel, and this is 1 by Z square is equals to 1 by R square plus 1 by X square. So this is the formula of equivalent impedance when these things are in parallel. From here we can see that 1 by Z square is equals to R square X square and X square plus R square, and this gives 1 by Z square is equal to R square X square. Now okay, let us write down below. This can give us, if I topple it, it is R square X square by R square plus X square. This is it. So what is Z? If I find Z, then it would be root of this. Then what we have? R XC by root over of R square plus XC square. This is what we have. Now what we need to do? We need to just put the value of R here and put the value of XC. And what is XC? This is important. XC is actually, XC is the effective resistance of the capacitor, and this is 1 by omega C. And 1 by omega C, what is omega? Omega is 2 pi F. F is the frequency into C. Now frequency has been given in our problem. This is 10 Hz as given in the problem. 10 Hz. So everything is clear. We can find Z, and then we will put it here and we will get the Z. So what we need to do? We have to do the rest of the calculation. Then Z is equals to R. R is 10 kilo ohm. R is 10 kilo ohm. Actually from here 10 kilo ohm and 0.01 microfarad. So it is, now 10 kilo ohm is what? 10 kilo ohm means 10 into 10 to the power 3 ohm, and that is 10 to the power 4 into XC. X is 1 by 2 pi FC. 2 pi F is 10 Hz. 10 into C. C is 0.01 microfarad. That means 10 to the power minus 8 divided by root over of R square. That means 10 to the power 4 whole square plus again X square. That means again 2 pi 10 to the power minus 8 whole square. This is it. Then we go and do our calculation. Z is equals to, this is 10 to the power 1 and 10 to the power minus 8. So it is 10 to the power minus 7, and it will go upside to become 10 to the power plus 7. So it is 10 to the power 11 by 2 pi. Okay, and this term is below. That means 10 to the power 4 square, that is 10 to the power 8, plus this is 1 by all this term squared. That means 4 pi square. 10 square is 10 to the power 2, and 8 to the power minus 8 square, that is 10 to the power minus 16. So this is what we have. Then z is equals to 10 to the power 11 by 2 pi plus, see one thing, that this is 10 to the power 2, this is 10 to the power minus 16, so it will become 10 to the power minus 14, and this 10 to the power minus 14 will go upside and it will become 10 to the power plus 14 upside, and downside there is 4 pi r square. Now we take LCM of these two terms, we want to add these two terms inside the bracket, so we do that. Now we take 4 pi r square, 4 pi square as LCM, so it is 10 to the power 8 into 4 pi square plus it is 10 to the power 14. I think it is clear. Okay, next we do the next thing that we do is z is equals to then 10 to the power 11 by 2 pi. From here 4 pi square, it is within the, it is under root, okay, so if it goes outside it will become 2 pi, and we have 4 pi square 10 to the power 8 plus 10 to the power 14. This 2 pi and 2 pi cancel, so we have z is equals to 10 to the power 11 by, now from these two terms we will take 10 to the power 8 as common, so we have 4 pi square plus 10 to the power, now from 10 to the power 14, 10 to the power 8 goes outside, so it is 10 to the power 6. Then we have z is equals to 10 to the power 11 by, what is the root of 10 to the power 8? It is 10 to the power 4. And what is left inside the root bar? It is 4 pi square plus 10 to the power 6. Now this term 4 pi square, that means 4 into 3.14 whole square, and that much is negligible with respect to the big value 10 to the power 6. It's very huge value, so this part is negligible and we neglect it. So what we are left with, we have 10 to the power 11, okay, let us cancel, this is 10 to the power 7 now, okay, 10 to the power 7 by root over of 10 to the power 6, because this is neglected, so we have only 10 to the power 6 inside the root. And what is 10 to the power 6? Root of 10 to the power 6, it is root 10 to the power 3, so it becomes 10 to the power 4. That means z is equals to 10 to the power 4. And we know that gain is what? Gain is equal to z by r1. Now r1 is already given, it is 1 k ohm. So 10 to the power 4 by 1 k ohm, that means 10 to the power 3 ohm. It is 10. That means gain is 10. And what is the phase shift of the output voltage? Obviously, since the input is going to the negative terminal, so the output will have a phase shift of 180 degree, that means pi. So obviously our answer is D. The gain is 10, the magnitude of the gain is 10, and the phase shift is pi, 180 degree. So answer is D. So the answer is D. Now one more thing that I wanted to tell you, that we had solved a similar problem like this in early videos, and that is the problem of December 2013. Problem number is 36. So if you find any difficulty in solving this problem, then you can refer to this problem that I had already solved. Okay, for now our answer is D. Thank you.